In November 2020 CSIR-NET physical science paper, 3 questions were asked from condensed matter physics. Let's solve these 3 questions. A tight binding model of electrons in one-dimensional has the dispersion relation given. Which of the following figures best represent the density of states over the range given? This question is based on the tight binding approximation. For electron, dispersion relation is given in 1D system. We'd want to identify the best graph of density of state for given region. The density of state represents the number of particles in per unit energy. If we rewrite this relation in form of wave vector k, then we get this relation of density of state. Now the problem is that the value of dk by dE in this relation can be calculated from the given dispersion relation. But we have no idea about the value of dN by dk. For this, we need to understand the behavior of electrons in a lattice. Several theories have been given to explain the behavior of electrons in a lattice. One of them is free electron theory. According to this theory, electrons move freely in lattice such as particle in a 1D box. Therefore, according to this theory, the energy of electrons in lattice is given by this relation, where n is the number of energy levels. Since electrons are fermions, therefore two electrons with opposite spin can occupy in one level. Means a total of 2n electrons can occupy in the n energy levels. Substituting this in relation to energy and rearranging n pi upon 2a is called Fermi radius. Rearranging and differentiating this with respect to k, we get the value of dN by dk 2a by pi. Now calculating the value of dE over dk from dispersion relation and substituting this in the relation of density of state, by solving we get this equation of density of state. Now if we verify its value for given range, then this gives finite result at pi by 2a while infinite result at pi by a, which matches the graph of option 2. A certain two-dimensional solid crystallized to a square monoatomic lattice with a lattice constant A. Each atom can contribute an integer number of free conduction electrons. The minimum number of electrons each atom must contribute such that the free electron Fermi circle at 0 temperature encloses the first Brillouin zone completely is. In K space or reciprocal space, the Fermi surface is a surface of constant energy EF, in which all the states are occupied by the valenced electrons, whereas the outside of the surface states are empty. In other words, Fermi surface has a boundary in K space between filled and empty states. According to the question, in a monoatomic square lattice having lattice constant A, we need to draw a Fermi surface such that it encloses the first Brillouin zone completely. For this, first we need to draw a Brillouin zone for a square simple cubic lattice. If the lattice parameter of a square lattice is A, its reciprocal lattice vector will be 2 pi by A. This reciprocal lattice vector defines the first Brillouin zone, which ranges from minus pi by A to plus pi by A. The area of this first Brillouin zone will be equal to just 4 pi square upon A square. Notice here the zone boundary is at pi by A distance from the center of the zone. In such a situation, we need to draw a circle on this center which will enclose the first Brillouin zone completely. If we draw a circle of pi by A radius, it will not be able to completely enclose the first Brillouin zone. In such a situation, we need to draw a circle whose radius is more than half of the diagonal of this square, means root 2 pi by A. Otherwise, circle will not be able to occupy the zone completely. Suppose the radius of the Fermi circle for electron is kf. But an interesting thing here is that the area of the Fermi circle depends on the valence of the atoms in the lattice. Means how many electrons are per atom in the lattice. If the atom is monovalent, then the area of the Fermi circle occupy only half of the total area of the first Brillouin zone. The rest of the area remain vacant. Rearranging this relation brings the radius of the circle to 0.798 pi by a, which is not sufficient to fully enclose the first Brillouin zone. If the atom is divalent, then the area of the Fermi circle occupies the equal area of the first Brillouin zone. But the problem is that this circle do not fully enclose first Brillouin zone. This circle do not crosses the corner of the zone boundary. The same thing happen even if the atom is trivalent. The Fermi circle do not completely enclose the first Brillouin zone. But if atom is tetravalent, then the Fermi circle encloses the first Brillouin zone completely. Since in tetravalent, per atom 4 electrons will be present. So option 3 is correct. A lattice is defined by the unit vectors a1, a2 and a3, where a is greater than 0 is a constant. The spacing between the 1, 0, 0 planes of the lattice is. In this question, 3 unit vectors of a lattice are defined. We want to calculate the interplanar spacing between the 1, 0, 0 planes of this lattice. Let us first understand the geometry of the lattice. This is not a cubic lattice because all 3 unit vectors of a cubic lattice remain the same and all 3 angles also remain 90 degree. While in the question, the 2 unit vectors a1 and a3 are the same, the magnitude of a2 unit vector is also the same. But talking of angles, the angle between a1 and a3 is 90 degree, but a2 vector is at 120 degree angle from a1 vector. This property is of a hexagonal lattice. In a hexagonal lattice, generally 2 unit vectors remain the same, but this is not mandatory. All 3 unit vectors can also be the same, but the angle always remain 120 degree. This is a hexagonal lattice. A hexagonal lattice requires 4 crystallographic axes to define. 3 axes A, B and D in the 2D plane at 120 degree angle from each other and C axis in vertical direction. If we compare the given vectors in the question with a hexagonal lattice, A1 vector will be in the direction of A axis. A2 vector is at 60 degree angle from minus I cap direction, while at 30 degree angle from J cap direction, whereby the direction of A2 vector is in the direction of B axis, which is at 120 degree angle from A axis. A3 vector is in the direction of the vertical C axis because this is in the K cap direction. In this way, the unit vectors defined in the question are a unit vectors of a hexagonal lattice. The spacing between two planes of a hexagonal lattice is given by this formula, where C is representing the vertical axis. With the help of this formula for 100 plane, the spacing between 100 plane of a hexagonal lattice comes under root 3a by 2, which is option 1.